All right, so now that we have our rotational kinematics equations under control, hopefully, we can move ahead and look at the relationship that I promised you that connects together torque and angular acceleration. And what we're going to find is that this is quite analogous to F equals ma. Because if we use these substitutions, that the x value, or the arc length, goes to theta, v goes to omega, and a goes to alpha, we go from our linear kinematics equations to our rotational kinematics equations. But what we're going to see is that with a couple more substitutions, we can go from F equals ma to another equation, torque equals I alpha. And so that's what I want to show you here. And I'm going to do it for a really simple example. So let's imagine here that we just have a point mass, simplest of all possible mass configurations, going around in a circle. It would be a point mass. And then as it goes around in a circle, we apply an acceleration, but that's due to a tangential force. So I apply a constant tangential force to the mass. And we'll assume that that force stays constant as the mass continues to accelerate and change its spin rate. So what we can say here then, using Newton's second law, is that F equals ma. But notice here that we are applying a force in such a way as to change the spin rate. So we can say then that the torque is equal to Rf times the sine of 90 degrees, or Rf. So if we multiply both sides of the equation through by R, what we get on the left-hand side then is torque equals mr times A tangential. But what's A tangential? A tangential is just alpha r from this equation. And so now we're just trying to put things, instead of having them in terms of force and tangential acceleration, because this is a tangential force, that's a tangential acceleration, we instead here are going to write it in terms of torque and alpha by writing that torque is equal to mr times r alpha, or mr squared alpha. And then we'll call this term that looks kind of like an inertia term, call this our moment of inertia. So we'll say the torque then is equal to I alpha, where I is defined as our moment of inertia. So inertia then, we know, is representative of some kind of a change in speed of some sort. In this case, it's our resistance to changes in spin rate. Notice that the I value for a point mass is proportional to the radius squared. So that if, for example, I were to double the radius, then the resistance to changes in spin rate would go up not by a factor of 2, but by a factor of 4, because of the fact that the radius is raised to the second power in this relationship. And so going up to the data projector, we see a definition then for moment of inertia, similar to the one that I just described, but put in a little bit different words. And you can check out the definition in the textbook as well. It'll basically say the same thing. And so for a point mass then, I is equal to mr squared. So what if we had a whole bunch of point masses like this? Okay? And let's say that we are going to neglect the mass of the connecting struts. Then for this kind of a problem, we would just sum up the individual moments of inertia about some central spin axis. Okay, and so in this case, with this baton that has massless struts, we can define we can call this mass 1, this mass 2, this mass 3, and this mass 4. Since this is our center of spin, all of our radius values are going to be measured with respect to that center of spin. So this would be R1, this would be R2, this would be R3, and this would be R4. So I then would be the sum of m sub I r sub I squared from I equals 1 to 4 for this problem. And so that's just a compact way of writing m1 r1 squared plus m2 r2 squared plus m3 r3 squared plus m4 r4 squared. All right, and so this is our way of writing the moment of inertia for a collection of point masses, but not for a continuous distribution of mass. If we had a continuous distribution of mass, like what I would have here with this rotating cylinder, then we require an integration. But we're not quite there yet. So we'll do this just for these point masses. And in this problem, m1 equals m3 equal to 0.2 kilograms, and m2 equals m4, which is equal to 0.3 kilograms. And all of these struts have the same distance, so R1 equals R2 equals R3 equals R4 equals 0.5 meters. So now we can plug in, and I'll combine together like terms. So we have M1 plus M2 plus M3 plus M4 times some generic R squared, because they're all the same. Okay, so it's a common factor all the way through. And so if we add these up, then we have 2 times 0.2 kilograms plus 2 times 0.3 kilograms times 1/2 meter quantity squared. Right, so here this is 0.5 times 2 is 1 times 1/4, or 0.25 kilogram meters squared. And so once we know what that moment of inertia is, then if we know how much torque is applied, then we can figure out alpha. Okay? And so torque then equals I alpha is our preferred relationship, in which if we use, for example, the equation F equals ma, this becomes our rotational equivalent. If force becomes torque, mass becomes moment of inertia, and as we saw before, the acceleration becomes alpha. So we end up with an equivalent mathematical relationship to F equals ma for rotational problems, being torque equals I alpha. And so this is kind of like our Newton's second law principle for rotational motion problems. Now, one other thing I wanted to point out is that this moment of inertia calculation is dependent on what the rotational axis is chosen to be. And so in this case, instead of spinning all of them about some central point, we could make our rotational axis go through the 2.2 kilogram masses. And so then our moment of inertia would be only involving the rotation of the 0.3 kilogram masses. Okay? And so in that situation then, the radii for M1 and M3 would be 0. And so we would just get 2 times 0.3 kilograms times 1/2 squared. And so that would be 0.6 times 0.25. And so that would only be 60% of the moment of inertia that we had in the last example. And so that would be 0.15. And that would have units again of kilogram meter squared. So it depends on which rotational axis you choose, which of these terms ends up being the ones that are involved with the sum. Now, in the next problem I wanted to look at, let's say that we have 2 bars here, and I just ask you to take it on faith that they have the same total mass. And so I'm going to go ahead and rotate this one. That looks pretty easy to rotate. So that's an indication of a smaller moment of inertia. Because remember, moment of inertia is resistance to spin rate. Now let's take this equal mass over here and rotate it. Oh, easy, not so easy. Easy, not so easy. So you go, oh, okay, well, you just have a weak left arm. So let's try it this way. Still easy, so no, that wasn't it. Hard. All right, so which one do you think has the mass configuration where the masses are closer to the center? Well, is it this one? I don't think so. The masses must be farther away from the center in this one compared to this one. Here the masses must be closer to the center because the moment of inertia goes like r squared. And so that, in fact, if we could look inside of these, is what we would see. We would see, in the case of the blue rod, that would be like B there, where that was harder to rotate. Notice how much bigger the radius values are. And the moment of inertia doesn't go like the radius, it goes like the radius squared. And so it makes it much harder to rotate. Whereas down in C, that was like the red rod, in which it was very easy to rotate. Okay, so that's the way that we deal with problems that have a mass configuration that can be considered to be a combination of single point masses. But now what I'd like to do is look at a few other mass configurations that are continuous mass configurations. In other words, continuous distributions of mass. This is more common because we're interested in an object and how it's going to resist changes in rotation that is a rigid body. So here we have a ring. Now that ring is going to be a sum of all of these different mass elements if we want to look at the moment of inertia. That would be the sum again of m sub I r sub I squared. But all of the m sub i's are the same distance away from the center. And so what we could do here then is we can just bring out the r as being constant. So this is the sum of the m sub i's times r squared. But the sum of all the little m sub i's for a thin ring is just going to be the total mass m times r squared. And so here we go again. This is the same expression for the moment of inertia as we would get for a point mass. And it's the simplest way to describe the moment of inertia for a continuous distribution of mass. Of course, this is idealized because we are neglecting the thickness of the ring. The fact that the ring does have a finite thickness indicates that there are slightly different r values going from one side to the other. But it isn't enough to really matter. You know, way less than 1% error by assuming that this is a thin ring. On the other hand, what if the mass were uniformly distributed throughout the interior? Then some regions would have mass that's closer to the center. Other parts of the cylinder would have mass that's farther away from the center. And so it would go like the radius squared. So for a problem involving a cylinder, what we have then is a moment of inertia that I think you could guess would be less than the moment of inertia for the thin ring. Because here with the thin ring, all the masses are out at the maximum possible radius. Whereas here, most of the mass is at a value of the radius that's less than the maximum radius, and so therefore the total moment of inertia should be smaller. And so the way that this is done mathematically is we set this up as an integral of r squared dm. Okay, where dm is some little mass element which we could think of as being a thin ring. And then what you have to do to solve this for the total moment of inertia is to write our little mass element as a function of r and perform the integration. I'm not going to do that here. I'm just going to write the result. This is equal to 1/2 m r squared, where r is the maximum radius of the cylinder, and the 1/2 factor is due to the fact that a lot of these thin rings, almost all of them as a matter of fact, are at a value of r that's less than they would be for the thin ring. And it's an infinite sum of thin rings that has different values for r for each of the thin rings. And so the net result then is equivalent to this object having essentially 1/2 the mass and being a thin ring. Okay, and so this is the result then for a cylinder. Now I for a thin rod, here again you would have some little dm. Let's say you're rotating it about the end. Okay? And if you rotate it about the end like that, then each one of these is going to be some different distance r away from the center of spin. So this would be like, for example, rotating a meter stick about the end like this. And so when we perform that integral, I about the end for a rod is equal to 1/3 ml squared, where L is the length of the rod. On the other hand, if we were to rotate it about some different axis, say about the center, we do that versus this. This one's harder to rotate about this axis, but easier to rotate about this axis. The reason, of course, is that the r values don't get as big, and the moment of inertia depends on r squared. So when all the smoke is cleared and we perform the integral with different integration limits, we get I rod about the center as equaling 1/12 ml squared. And so these results, unless I asked you on an exam to derive these results, which I don't think I really have time to do with this new format, I would give you the values for the moment of inertia that you would need to solve the problem. But I wanted you to see how it sets up, and I know that probably some of you have already done this in your calculus classes. This and center of mass seems to be the two calculations that I've noticed that are done most in the calculus classes that you had before you took this class. But neither one of them is really going to involve a physics kind of a calculation, either of center of mass or of moment of inertia. I'll just give you what the centers of masses are and what the moments of inertia are for the purposes of any problems that you might want